Hello all, I'm back with another video, and as you can see in your screens, this is going to be about solid material properties, which corresponds to topic 2b from the Unit 1 AS level physics. But as I said in previous videos, I suspect that this is the exact same material used for the Edexcel AS exams in England and probably other A-level specs. So let's get started. So here we will study, okay, so here we will study how solid materials respond to stretching, okay. So we will study how solid materials respond to stretching. And this is something that I often omit doing, and I think it's really important in physics. So I guess answering why would anyone study this thing. So the materials of solid matter, and especially the things that we will be studying here at the AS level, such as stretching, a response after tensile forces or compressive forces and stuff like that. These are things that engineers use when they build things. So a civil engineer, for example, needs to know these things by heart. I mean, when you build a building, you need to know how materials respond to pressures, smearing forces, winds, and stuff like that. So you want to know whether a building will oscillate and by how much and stuff like that. And the same goes for aerospace engineers and mechanical engineers, anybody who uses materials to build anything, okay? So it's really important to understand the properties of materials. But let's dive into what you actually need to know here at the high school level. So we will start with the easiest example, which is the spring, okay? So you're all familiar with a spring. Let's say it has a length L, okay? We don't need this arrow, okay? So it has a length L, and we somehow apply a force, okay? And we stretch it. So we know that if we apply this force, if this was the initial length, okay? So this was the initial length L, the spring is gonna stretch by delta X, right? This is something that everybody knows. So you can think of springs as one-dimensional objects, meaning that they stretch in one dimension, okay? We will come back to this in a moment. Now, the same happens to two-dimensional materials, right? So if you have a wire, okay? So maybe you have a wire that has some cross-sectional area, okay? And you apply a force, or maybe it's a rubber band or something like that. The same thing is gonna happen to the wire or the rubber band, okay? So you will have some extension, let's name it delta L, okay? So this is the extension, small one, okay? So wires and rubber bands. Now we treat this as two-dimensional materials, meaning that whatever happens to their cross-sectional area, okay? So, and this is the cross-sectional area. Let's draw it with green. So that's the cross-sectional area, okay? And another thing that can happen to two-dimensional materials, but also in springs, you can compress them, right? So maybe you have, I don't know, a concrete beam or something like that, okay? So let's try to make it look like a box. Not the best designer in the world, so maybe you apply some. By the way, this force that exercises pressure on this concrete wall is called a compressive force, whereas the force that stretches the wire above is called the tensile force, okay? So if you push it, okay, if you compress it, okay, I'm exaggerating the effect here, but you will have a compression of the concrete block, okay? So you will have a compression delta L, okay? Okay, compression. And I'm gonna write it in parentheses. This is a concrete block. Okay, so when we deal with springs, we use the Hooke's law. Okay, so Hooke's law applies to springs, and this is what we will study first. And after we study Hooke's law, we will talk about the Young's modulus and stress and strain and stuff like that. Okay, so this applies to two-dimensional materials that I'm showing here. So this is okay, Young's modulus, stress, strain. Okay, we will study this once we talk about springs. So let's start with Hooke's law. So Hooke's law describes the force experienced by springs and materials that can stretch and then return to their original position. Okay, so this is what Hooke's law studies, and we will quantify this in a moment. So before we quantify it, let's do a thought experiment. Okay, so maybe we have some ceiling, okay, and we have a spring, okay, and we hang some mass by this spring, okay, so it will extend by some amount delta x, okay. Now if we use the same exact spring, okay, but we now apply twice the mass, okay, 2 times mg, then the same spring will stretch by 2 times delta x, okay. So, and you can also study this experimentally, of course, and you're gonna arrive at the same conclusion. So this tells us that the force is proportional. Let me write it like this. I always have trouble with this symbol. So, okay. So F is proportional to delta x. And in fact, Hooke's law tells us that F is actually equal to some constant K times delta x, okay? And this is Hooke's law. So the force is proportional to the displacement. So, and now to talk a little bit about that constant K. So the larger the K, the harder it is to stretch the material. Okay. Now the units for K, so units, so K, if we solve for K, we have F over delta X, right? So if we use, remember those brackets that I use to denote that we are dealing with the with the units of some physical quantity. So the units for K, let's keep this, so K is newtons over meters, Okay, and if we want to break it further down to the base units, where you have to recall that the Newton is 1 kilograms times meters times seconds to the -2, and then we have meters in the denominator, so the base units for K are kilograms per seconds to the -2. All right. Now let's study. What did I do with my? Okay. So it's a mess. If you come here to my desk right now, you're gonna see a total mess. So, and there is a high chance that I will be moving soon. So I don't know how I'm gonna keep posting these videos, but we will solve that problem once we arrive at it. So the next thing I want to talk about, which is really important to know, is the plot of force versus displacement. So let's draw the plot. Okay. Great. Okay. So force in newtons and let's say delta x in meters. So if you do an experiment, you will find that you have a straight line relationship, okay, up to some point. So starting from 0, you will see this linear relationship, but at some point things stop being linear and you will see something like this. Okay, and if you continue stretching, you will see something like this. All right, so this is exaggerated, so let me draw it again. So something like this. Okay, great. So in this region, let me mark some important points here. So there is this point over here, which is important. We will talk about it. Maybe let's make it like that. Okay. And then there is another point like this. Okay, no, maybe there. Okay, that one, then that one, and then that one. Okay, let's talk about all these points. So this point is called the limit of proportionality, which means that in this region, Hooke's law applies. Okay, so because Hooke's law applies in this region, we know that the gradient of this curve is equal to k. Okay, now this point over here is called the elastic limit. This point over there is called the yield, and this is called the failure. So let's call this A, B, C, and D, and I'm gonna write down here. So A, as we said, is the limit of proportionality. Which means that Hooke's law applies, and the gradient is equal to k. Now B is called the elastic limit. Okay, if force stops applying, the spring / material will return to its original position. Okay, this is what it means. This is what elastic limit means. The next point is the yield. Okay, so yield point. So the material starts breaking. Okay, so the material gives, meaning that it starts breaking. Okay, and then D is the failure, which means that the material breaks. Okay, so and for the yield point, you can also write the word necking, though that really applies to, okay, let's erase it actually. So necking means that the material becomes really thin at one point and it starts breaking. So, but anyway, the yield actually encapsulates what's actually happening, which is that the material starts breaking down pretty much, okay? So let me check something before we move on. All right, so, okay, so this is what the plot of force versus displacement will look like. So sometimes in exams, they show you all this plot, I mean, with including the points A, B, C, and D, and they ask you questions related to those points, okay? But most of the times they will not show you that, maybe. I don't know. We'll have to go through more papers and see. But anyway, another important thing is the energy stored in a spring. So energy stored. If we plot again the plot of force versus displacement, okay, we're gonna plot only the straight part, okay? And if we draw a line there, so let's okay. So if you draw the force versus displacement graph, we will find that straight line. And let's talk about the area under the curve. So the area is equal to 1/2. It's a triangle, right? So it's 1/2 base, which is delta x, times height, which is force, okay? Force times delta x. But force times displacement is work done, right? So that's actually the energy stored. So energy stored. Okay, so why is it 1/2 and not fully and not just F times delta x? For this, you have to use the argument that half the energy is gone in actually stretching the spring. Okay, so I think that's the argument. So so the area is the energy stored, and we actually officially write it as W elastic or E elastic is equal to 1/2 F times delta x, and the units are joules, since 1 joule is 1 newtons times 1 meter, okay? Now let's talk a little bit about more advanced graphs that you might see. So maybe a graph will look like this. So in some problems, they might ask you to find how much energy is stored in a spring or a material that was stretched. So you will have to find the area under the curve. So area is equal to the energy stored. How are you going to find this area? By counting squares. It's a very popular problem that I see at the A levels all the time. So you will have to literally, I'm sorry about that, but you will have to do it. So you will have to measure 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. Then when you encounter things like this, so this one and this one make one whole, something like that. It's an estimation problem. So you will have to count the squares, and then you will have to find the area. So area of 1 square times all the squares is equal to the energy stored. Okay, And another advanced concept that appears mostly in rubber bands. So let's write it down. Rubber bands and the concept of hysteresis. Okay, it's a Greek word, and as a native speaker, I have to explain. So hysteresis means to delay something from happening. So in some materials, you will have a force versus displacement graph that will look kind of funny. Let me show you. So when you stretch it, maybe it will look like this, okay? Okay, so, and I'm gonna put arrows denoting that initially we stretch it, okay? So the energy stored in this material as we stretch it is, like always, the area under the curve, right? Let me erase that though. But when you release it, it doesn't really come back to its original position through the same curve. That does not happen, okay? So what actually happens is that it returns to its original position like, oops, like this. Okay, so I'm gonna put the arrow that when it returns, it follows that path, okay? So this is actually called the loading, and this is called the unloading. Okay, and since the area under the unloading curve is the energy we get back, okay? So when it loads, we get that energy back. But that energy is less than the energy we have to expend when we stretch the material, okay? Therefore, we have an energy loss. So the area in between these two curves is the energy lost, okay? So I hope this is clear. If it's not, ask me in the comments and I will try to explain it again. So this is energy lost in the process, okay? And it's usually lost in thermal energy, okay? And again, if they ask you something like that in an exam, you will have to count the squares in between these two curves. Again, when we load it, the energy stored in it is the area under the curve. When we unload it, we get some of that energy back, but not all, okay? And therefore, we lose some energy in the process, which is the area in between these two graphs. And this is a very advanced concept, but it did appear in past papers, so please pay attention to it. Okay, let's move on. Okay, before moving on to talking about Young's modulus, stress and strain and stuff like that, I want to take a moment and talk about springs in parallel and in series. This goes in the old spec, but it doesn't really hurt to know at least the basics. So we will just quote the results that it's good to know. I doubt it will appear in a test, but you never know. So if you have, this is called springs in series. So if the first spring has a constant K1 and the second one has a constant K2, then the total K, the total spring constant is given by this expression. Okay? 1 over K total is 1 over K1 plus 1 over K2. But if they are in parallel, so if the two springs are connected like this, so maybe there is a rod that makes them connected. So if this spring has a constant K1 and this one has a constant K2, then the total constant is K1 plus K2. Okay, so when you connect them in parallel, in other words, they get stronger, okay? So again, this was in the old spec, but I'm just mentioning it in passing, doesn't hurt. So let's move on to talk about stress, strain, and the Young's modulus. Actually, why did I put a slash there? A comma is better. So stress strain and the Young's modulus. And by the way, it's the same Young as Young's double slit experiment. So same person. So stress describes situations where there is either a compressive or a tensile force. So stress describes situations where there is either a compressive or a tensile force exerted on a 2D material. Okay, and when I say a 2D material, we mean on the cross-sectional. So this force is exerted on the cross-sectional area. Okay, so we drew this in the beginning of this lesson, but let's do it again. So if this is the cross-sectional area and we have a force exerted on this material, then we have a stress. And by the way, when we pull, that's a tensile force. When we push, that's a compressive force. Okay. Is there anything else? No. Okay, let's actually define it. So sigma is how you denote stress, is given by force over cross-sectional area. So you see that it's similar to pressure pretty much, okay? So the units are pascals, right? Because we have newtons over square meters. Now, if you want to work out the base units, again, we have to analyze the newton, which is not a fundamental unit. It's not a base unit. So 1 Newton is 1 kilograms times meters times seconds to the minus 2, and then we have meters squared in the denominator. So in base units, a Pascal is equal to 1 kilogram times 1 meter to the minus 1 times seconds to the minus 2. All right. Let's do a brief example, a quick example to just you guys get a feeling of the order of magnitude of these things. So let's say that we have a wire. Okay. This is a wire. This is the cross-sectional area. The diameter of this wire, D, is 10 millimeters, and we apply a force of 2,000 newtons, okay? 2,000 newtons is a force equivalent to the weight of 200 kilograms, okay? So 2 persons, maybe 3 persons, okay? So the weight of 3 persons exerted on a small area like that of some metallic wire, say, okay? So this is actually possible in real life, okay? So let's find the stress. Stress is force per cross-sectional area, and the cross-sectional area is pi times d over 2 squared, because the radius is equal to half the diameter, right? So the force is 2,000 newtons, and half the diameter is 5 millimeters, which is 5 times 10 to the negative 3 squared, and then we have meter squared. So this is actually equal to 25.5 megapascals. Okay, so that's a huge stress. Okay, and yeah, this is a very quick example. Let me write something. So note the cross-sectional area in problems that you might be given. The cross-sectional area might be square, might be square or rectangular. Okay, so if something like that happens, don't panic. It's the same idea. Stress is force per area. You calculate the cross-sectional area and you move on. Okay, so that was stress. what is strain? So strain is equal to the extension of a wire. So when we pull it, it extends by some amount over the original length. Okay, so over the original length, or mathematically it's denoted with the Greek epsilon, okay, which is equal to delta x, the change, okay, the extension, over L. Sometimes they write it as delta L over L. It's the same thing. And notice that it's dimensionless, right? So meters over meters is the units. So this is equal to 1. So strain is dimensionless. Okay, so so again, let's demonstrate briefly what strain is. So I have this piece of wire and I pull it using a tensile force. Okay, so this was the original length and this is delta L. So strain is delta L over L. Okay, now we can use stress and strain to define the Young's modulus. So use stress and strain to define the Young's modulus. All right, so the Young's modulus is defined by this capital E, okay, and it's given by stress over strain, okay. So notice this will come later. So no, I'm gonna write it. Let me finish and I will write something that it's important. But anyway, if we plug in the definition of strain, which is force over area, actually let me write it like this. So force over area, and strain is extension over the initial length. We also see that the Young's modulus is equal to force, let me see, times L over area and delta. Okay, yes. And what are the units of Young's modulus? It's again Pascal, right? Because you have force per unit area, so pascals, and then the L over delta L is still dimensionless, okay? So that's Young's modulus. Before I write the next thing, I want to write that note. Sigma is given by the Young's modulus times the strain. So when you plot stress and strain graphs, the gradient is the Young's modulus, but only in the linear region. So let's write it like that. So sigma, okay. So in a stress versus strain graph, the gradient of the linear part of the graph is E. But as we will see later, when you plot stress versus strain, you indeed have a linear region, but then you also have weird things like this, and we will talk about it. But in the linear region, okay, linear means straight line, okay, so in this region, the gradient is equal to the Young's modulus, okay? Now, the Young's modulus expresses the stiffness of material, okay? I mean, to describe it physically. So Young's modulus describes or expresses, I think it's better, so expresses the stiffness of a material. Okay, it's a constant meaning that samples with different shape or length, but made of the same material, have the same Young's modulus. Okay, so I hope this is clear. So if we have a really thick iron wire and a really thin iron wire, the Young's modulus is the same for both wires. Okay, it's a constant for the material. Okay, now if we solve for delta x, we see that this is equal to F times the length over area times the Young's modulus. Okay, so if the force increases, then delta x increases, which makes sense. If the area increases, delta x decreases. Okay, so this is something you don't expect, but it makes sense, right? A thicker wire will extend less than a thinner wire under the same force and length and Young's modulus. Okay, I hope this makes sense. If the length of the wire increases, then delta x also increases. Okay, which makes sense. It's easier to pull a longer wire than a shorter wire, given that the cross-sectional area is the same and so on. Okay, and one last thing, if the Young's modulus increases, delta x also decreases. So meaning that a stiffer material, like I don't know, I'm trying to think, nothing occurs. But anyway, if a material is stiffer, it's difficult to pull it and extend it. Okay, so these are good things to know. Let's move on though, okay, and talk about stress and strain graphs. So stress, strain graphs. Okay, we already talked about this briefly here, and I told you that in the linear region, the gradient of the stress-strain graph gives you the Young's modulus. Okay, the stress-strain graphs describe how materials behave when we increase the stress or the strain. Okay, and they tell us many properties of this material. So let's get started with an example. So this is the stress, and this is the strain. Okay, so sigma and epsilon. Okay, so as I said, all materials have this straight region in the beginning. Okay, so let's mark this as point A. Okay, as we increase the stress and the strain, we start seeing a region like this, slightly bent, and I'm gonna mark this as B. Okay, then if we keep increasing, we will see something like this. Okay, B disappeared, so let's do it again. Okay, so that's point C now, and I will talk about these points in a moment. And then if we keep increasing, we will see something like this. Not like that, I'm sorry. Something like this maybe, okay. So let's call this, okay, and then we have something like that. Okay, great. So let's call this point D, and this point is E. Okay, so let me see how I want to do this. So starting with point B, this is called the elastic region. Okay, and this is called the, if we extend up here, this is called the plastic region. Okay. And then if we draw another line here, this is called the proportionality region. Okay, so in this region, the gradient of this graph is equal to the Young's modulus. My handwriting became horrible again. I'm not trying. Okay, so the gradient is equal to the Young's modulus because remember that sigma is E times E, epsilon times the Young's modulus. Okay, but this only applies in the linear region where we have elastic behavior. Okay, now I'm gonna just name these points maybe and then explain them below. Or maybe no, it's gonna become too crowded, so I'm gonna just explain them below. I want to also mark another region here. So this region between D and E. Okay, so this is where necking occurs. Necking. Okay. Now let's go explain all these points. So A, in up to point A, the material behaves elastically. So we're gonna mark it as elastic behavior. Now B is called the elastic limit. Okay, elastic limit. If F is removed, okay, if the force is removed, the material returns to its original position. Okay, now C is called the yield point. Okay, so the material undergoes a sudden increase in extension. Okay, so the atomic substructure changes. Okay, so atoms rearrange internally. Okay, so rearrange and move to new positions. So yield point means that the material starts yielding, giving, like it starts getting destroyed, right? Okay, it extends a lot and so on and so forth. For those of you who played with materials, it's the yield point is where when you extend a material, it starts stretching uncontrollably, okay? So it breaks pretty much, it starts breaking, okay? So material yields and we have permanent deformation. Okay, now D is the ultimate tensile strength. So D is this point over there, okay? It's the highest possible stress, the material can withstand. Okay, and sigma max is then F max over the cross-sectional area, okay? And then E is the fracture point, okay? So fracture. The material simply breaks. It doesn't extend anymore. It just breaks. All right, so, and one last thing. So necking, which I mentioned in the graph between points D and E, so this region over here, okay? Necking is a phenomenon that many materials have. I don't think, do all materials have that? No, brittle materials don't have that, but metallic materials certainly do. So necking is when, you know, this is the material under normal circumstances, right? But necking is when, because you stretch it, the material becomes really thin at one point. So this is what necking is. Necking, the material becomes really thin at one point. All right. Now let's, what else do I want to talk about? So really important graphs. A question always appears in the AS level test for Unit 1. So usually they're going to show you a graph and make you describe it or derive the Young's modulus through the gradient, stuff like that, but they always have a problem like this. Now let's talk about brittle and ductile materials. And we're gonna talk about these materials through two graphs. So ductile materials, okay, can sustain large strain or deformation before fracture. I don't know why my iPad behaves like that sometimes. So before fracture. So metals are the best examples of ductile materials. So if we plot the stress and strain graph, okay, it will look like this. So that's the strain part, the straight part, I'm sorry, and then something like this. Okay, so ductile materials have a large plastic region or plastic deformation. All right. Now, brittle materials, usually bricks, concrete, materials like that, stone, marble, that kind of thing. So brittle materials, okay, have actually very little to no yield. So no plastic deformation. So no plastic deformation. Okay. And they can fracture without notice. Fracture without notice. And the examples are, let's write it in parentheses, so concrete, stone, marble, granite, and stuff like that. So if we plot the stress and strain graphs, I'm sorry, it's not a plural, it's just one. So a brittle material will look like this. It will have a really, I didn't want that. It will have a really large Young's modulus because the gradient is steep, as you see, but then something like that only. Okay, so this is a brittle material. This is another brittle material. Okay, so the green material has a smaller Young's modulus. And again, I remind you that the ductile material will look like this. Oops, that, and then something like that. So the ductile material has a large plastic deformation, whereas the brittle does not. Okay, and this is all I wanted to talk about with regards to brittle and ductile materials. And another important concept, I never saw it appear in an exam, but it's good to know. So the area under the curve, area under the stress versus strain graphs. Okay, so what kind of quantity does the area represent? So sigma, so stress and strain, so maybe a graph looks like this. So the area under the graph is proportional to sigma times so stress versus stress times strain. I'm sorry, I don't know why I got confused. So again, you will have to count squares to find this. Count squares. Okay. Except for the linear region. I mean, the linear region, you can use the area of a triangle. So for example, in this graph, I mean, this area over here, for example, is a triangle, right? So anyway, so what kind of quantity does this represent? So let's use the units. Stress has units of newtons times, over meters squared. And then strain is dimensionless, but let's just write it as meters over meters, right? So this is the stress and this is the strain. But if we multiply, we have newtons times meters over cubic meters, okay? So that's a volume in the denominator. And then recall that newtons times meters is joules. So joules over cubic meters. So the area under the stress strain graph represents energy stored in the material over volume, okay? So the area, let's write it down. So energy over volume. So the energy, sorry, the area, not the energy. So the area under a stress versus strain graph represents the energy stored in a material per unit volume. So if they ask you a question like that, find the energy stored per unit volume in this material, you will know what to do, okay? And then if you multiply that energy you found with the volume of the material, and to find the volume, they should give you the, I don't know, if it's a cylindrical wire, they should give you the length and the radius, so you can find the volume, okay? If they give you the volume, you can find the total energy stored in a wire, for example, okay? So I think that's cool to know, even though, again, I didn't see it in any past paper. But maybe if someone from the edXL, the Pearson organization, etc., is watching these videos, please sponsor me. That's the first thing. And secondly, maybe I just give you ideas of problems to give to students in a Unit 1 test. Okay. This concludes the lessons on Unit 1. I will try to see what I can do about Unit 2 lessons. I have some past papers I can upload gradually. And this channel started growing a little bit, but eventually, as I said, the plan is a very loose plan for now because I don't know. Still, I'm learning how to make videos. I'm learning what people need, etc. But the plan is to eventually finish with all the material for units 1 to 6. And then I will just solve past papers. But gradually I will start solving some problems that is university level or graduate level physics. So, and maybe eventually I will talk about other topics as well. But anyway, thanks for watching. Please like and subscribe. Please help me grow this channel. And funding is always welcome. So thank you guys, and